So we have finished chapter 2, in which we covered the first law of thermodynamics, and we also covered how to evaluate Q and W individually. Now we will be starting off with chapter 3, that is to evaluate properties. So properties are what properties do. They help us characterize a system. So properties help us to characterize the system. So let's suppose that the room that we are sitting in is our system. So how can we know the system? So this room is characterized by the dimensions. Let's say it has a width, length and height. So these are dimensions which tells us the area and the volume of the room. But what are the thermodynamic properties that help us? So thermodynamic properties are temperature of this room, pressure of this room, the specific volume of air inside this room. So if we know these properties, we can know many other properties. For example, if we know these properties, we can obtain internal energy, enthalpy, and many others. So in this chapter, we would learn how to obtain the properties. So before we get on to that, now what is a phase? A phase refers to a quantity that is homogeneous throughout in chemical composition and physical structure. So phase is, for example, if we have a container having ice, these are ice cubes, they are surrounded by water. So water and the ice cubes both have the same chemical composition, that both of them are H2O. However, their physical structures are different for liquid and solid ice. So these are two different phases. If we start heating this water, we would start having water vapors inside this container. Now, this water vapor would also have the same chemical composition, so H2O, however, it would have different physical structure. Next thing is homogeneity in physical structures mean that the matter is all solid or all liquid or all vapor. So homogeneous means, so this container that I have drawn is not homogeneous because it has all the three states of matter. It has solids, it has liquid, it has gas. However, a container only having one of the states would be regarded as homogeneous, that it would have the same physical structure throughout. Next is a pure substance. A pure substance is uniform and invariable in chemical composition. This substance, this container having three phases of matter is a pure substance. Though it has three phases, but each of the three phases have the same chemical composition. So a pure substance can exist in more than one phase, but its chemical composition must be same. Chemical composition must be same. Temperature and specific volume are independent, determined. So temperature I highlighted earlier and pressure are independent. And whenever we know two properties, we can obtain the third property. So this is the most important thing I want you to remember, that whenever we have two properties, or to be more exact, two independent properties, we can obtain the third property. So now look at this diagram on the right. The diagram on the right is pressure versus specific volume versus temperature. Now if we break the 3D diagram into a 2D diagram, figure B and C, those are easy to explain. So starting with pressure versus specific volume. So pressure versus specific volume. So for a liquid, the first thing we draw is this vapor dome. So this vapor dome means that three phases of matter. This is solid, this is this line, so this is liquid state, this is liquid plus vapor, and this is vapor state, which basically means that, for example, if we have a liquid, we start boiling it. When we start boiling it,
Sir, can you kindly repeat that?
it changes from liquid to vapor. As we start boiling, at boiling point, the phase will start changing from liquid to vapor. And when all the material is in vapor state, it will again, so liquid plus vapor, and then eventually it's all vapor. So this liquid, this line that I have drawn is a constant temperature line. For example, if I ask you to draw a constant specific volume line, so it would look like this vertical line. If I ask you to draw a constant pressure line, it would be this horizontal line. But for PV diagram, constant temperature line would be this line, so this line that I have tried to highlight. So this is the constant temperature line. So coming back to the statement, so for a single phase, a state can be fixed by any of the two properties. It can be pressure temperature, or it can be volume temperature or pressure volume. So any state, if we know two properties, let's say we know temperature and volume, we can find pressure. So for a mixed phase, temperature and pressure are not independent. So what is a mixed phase? This liquid and vapor, in which liquid and vapor both existed. In it, temperature and pressure are not independent, which basically means, so I'll draw this diagram again. So pressure versus volume. This is a vapor dome and this is the line of constant temperature. So in mixed vapor, let's say this point over here, the pressure and temperature are not independent. So this line over here is horizontal line. On this horizontal line, pressure and temperature are not independent. Why they are not independent? Because suppose that we know specific volume is this amount, and if we want to find this corresponding pressure, we get this pressure. Suppose the specific volume changes to this amount. Again the pressure remains the same. So pressure, volume for a mixed phase are not independent. Now a state can be fixed by specific volume, temperature or pressure. What is a state? So let's say this is point 1. So this state, so this is a state. It is defined by its properties. So three phases can exist on a triple line. So three phases, solid, liquid, gas, can exist on a triple line. Next is saturation state, a state at which change begin or end. So this line here are saturation states. So this is where liquid starts changing to liquid plus vapor, and on this line liquid vapor starts changing to vapor only. So liquid is changing to liquid plus vapor and then vapor only. So this we know from boiling, that first we start boiling water, it reaches the boiling point, and then we start increasing temperature, and then we start giving heat. All of it does not get boiled. Instead, all of this energy is converted, the latent energy, after all of the vapor has boiled, then again we would see that the temperature starts increasing. However, we can convert directly from liquid to vapor. This can happen if we are above this critical point. If the pressure and temperature are above the critical point, then liquid can be converted directly to vapor. Now looking at, so previously I had drawn pressure versus volume. Now this graph is temperature versus specific volume. So similar to pressure versus volume, you would draw a vapor dome. So if I were to ask you what is the line of constant volume, you will draw a vertical line. If I ask you what is the line of constant temperature, you would draw a horizontal line. Now what you need to remember is the line of constant pressure. So it would look like this line of constant pressure. This is opposite to the temperature line, constant temperature line that we draw previously. So in the constant temperature line, it was downward sloping, and in the mixed region it was horizontal, but in the liquid and vapor region it was downward. Now the constant pressure line is upward sloping. I want you to remember this for now, and in later we would understand why it is upward sloping here and why is it downward sloping there. So this line, so the same thing has been drawn over here. So you have liquid region, liquid vapor, and vapor region. As we start heating, this region over here is called subcooled liquid, or you can say liquid. Then we reach liquid vapor region, and as we keep on heating, all the liquid vapor reaches vapor only, and after 100% vapor we have again. So this region on the right hand side is called superheated region. So we are changing from subcooled liquid to superheated. So this subcooled region is also called compressed liquid region. So it is also called compressed liquid. So why it is compressed liquid region? So in the compressed liquid region, if you look at this region over here, its density, its specific volume changes very less as compared to the temperature change. The specific volume changes very less. So it is difficult to compress. So it is called compressed liquid region. So if we were to divide this vapor dome into three regions, it is region A, region B, and region C. So this liquid region is A, this vapor plus liquid is B region, and this is C region. Okay, so at F it is 100% liquid. and at G it is 100% vapor. So mass of vapor at F is 0%, let's say 0%, and mass of vapor at G is 100%. That we are changing from liquid to vapor. So if between these 2 points we have a thing called quality. This X is quality of the mixture, which basically is mass of vapor divided by mass of liquid plus mass of vapor. So this is again the vapor diagram. So here X is 0 and here X is 1. So here mass of vapor is 0. So X is equals to 0. And at the other end, mass of vapor, mass of liquid plus mass of vapor. This was x1, this is x2. At the other end, the mass of liquid is 0. So mass of vapor divided by mass of vapor is 1. So we are changing from liquid to vapor. This line over here is called saturated liquid. Saturated liquid means that it is 100% liquid. This line here is called saturated vapor, which means that it is 100% vapor. Next is interpolation. So interpolation is what you have, if you have done in previously. So interpolation is that we know. So at the back of the book there are tables, there are different tables. So let's see, at the back of this book for water we have pressure equals 10 bar and we know at temperature 200 this is the specific volume, and temperature 240 this is the specific volume, and we have to find specific volume at an intermediate temperature of 215. So 200 versus specific volume is plotted here and 240 is plotted here. So these two things we know from the tables at the back of the book. For anything between them we would have to use interpolation, which basically means that we are substituting them and we are assuming that it is linear between the 2 points. So if we assume linear between the 2 points, we will be able to do it. So in the next class, we would derive this, how to derive this formula.